Welcome everyone to this week's seminar. Today's speaker is Geir Isaksen, and the title of his talk is A Method for Calculating Protein Stability. And as always, I will ask people in Oslo to not make noises while the presentation is going, because they are easily picked up. Are you ready in Oslo? They don't seem to hear us. Can't see you.
They heard us 5 minutes ago.
So you hear us now? Okay, good. Let's begin. Welcome.
Okay. Thank you. So as Magnus said, the title for today's talk is A Method for Calculating Protein Stability. This is a project that I'm mainly doing with Professor Johan Åquist at the University of Uppsala. So we started this project in August when I took my wife and my 3 kids, and we moved down to Oslo to stay there for 6 months. So we came back now in February. So I will try to present to you the why and the what's in this project. So what do we want, and why do we want this, and how do we get it, and the challenge of getting it. And then perhaps the most interesting question is, what did we actually get? So what we want is a method to enable us to predict the stability of proteins from mutations. We want to do a mutation, and we want to be able to say whether or not this mutation is stabilizing or destabilizing the protein. So we are in principle interested in the relative stability of the protein. But first of all, this might not be intuitive to everyone, but the stability of a protein is defined as the net free energy difference between the native state, that is the folded protein or enzyme, and the denatured state, which is the unfolded. So you can get an estimate of the change in the free energy of folding or unfolding the protein by calculating the difference between these 2 states. At least the points I came up with when I was writing this. And in our group here in Tromso, together with Björn, we have for quite some years now been working on the temperature dependence of enzymatic reactions, and been looking at how enzymes can adapt to different temperatures. And what we typically see here is that, for example, an enzyme which is cold adapted has an activity optimum which is shifted to a lower temperature compared to the warm adapted. Now this plot here is a bit exaggerated. They're not that separated in reality. But so as the temperature increases, the activity drops, first for the cold adapted enzyme as a result of destabilizing the enzyme, so the enzyme starts melting. So it's a more unstable enzyme in that respect. But still, the 3-dimensional structures of such enzymes are typically, when we look on them, they look identical. So these are differences on the amino acid level. And then the question is, why do we want to predict this? Why would anybody be interested in predicting the stability of proteins? So we know that when we do a mutation to an enzyme, it can obviously affect the catalytic barrier, so the activation free energy of the enzyme. And when experimentalists work in the lab, this is what they are measuring. They are measuring the reaction rates of the enzyme. And they do a mutation, and they see if they can see a change in the reaction rates. And what often happens is that if you don't see a change in the reaction rates, they conclude that this mutation is not interesting, and often it's ignored. What we have seen and found through the recent years of research that we have been doing in our group is that this is not entirely true, because we have seen that we can do modifications to the enzyme, and particularly in regions which are far away from the active site. And this has also been shown experimentally that these modifications doesn't necessarily have to affect the activation free energy or the reaction rates of the enzyme. But what we see is that they have a great influence, or they can have a great influence on the entropy balance of the activation free energy. This is what.
Yes.
There is quite some noise from a microphone in the room. Is there some microphone that can turn off in the room now, or?
No. The only microphone we have is a microphone that is suspended from the ceiling. And,
okay.
We can only, I guess, adjust the volume of that one, but there's nothing else to do about this. I would encourage everyone to not make any noise.
We just had some people coming into the room, so it was probably not.
Okay.
Yeah. Okay. You can stand closer to the microphone.
But the camera.
Yeah, we had the camera there.
Yeah, so we can hear Geir perfectly, except when people move too much.
Stop moving.
All right, don't move.
So be still. Okay. Thanks.
Okay, so where was I? Okay, so modifications to the enzyme or the protein can affect the entropy balance, and this in turn is what determines the temperature optimum of the enzyme. So by tweaking the enthalpy and the entropy, we can shift the temperature range where the enzyme is working. So this is something which is important to include in this type of studies. So we have developed through the last years now tools to calculate activation enthalpies and entropies for enzyme reactions. So this is something that we already now have in our toolbox. And we have for quite some time now been discussing that the natural next step now is the ability to actually calculate protein stability. So the long-term goal in all of this is to be able to do computer-aided enzyme design. So we design our enzymes on our computer to perhaps a target structure and a target function, and this of course will have big bioengineering and biomedical applications. So I think that probably the easiest story to sell is that, I mean, a lot of proteins and enzymes are involved in diseases, and many people believe that we can design also enzymes to be part of the cure. But it helps very little if we sit on our computer and optimize the activation free energy, the activity, and the temperature where this enzyme is supposed to work, and then somebody in the lab takes this and tries to produce it, and it's not stable. I mean, it won't even become an enzyme. So it becomes sort of interesting to also be able to say something about the protein stability when we do this. Plus that we can, of course, learn something about the adaptation of enzymes through evolution, which is interesting in itself. So this is the tool we are missing and trying to target right now, is to predict protein stability. And the challenge here is, of course, as with anything else we are doing, is that proteins, they're big. I mean, so per definition, a protein is defined as something which consists of more than 50 amino acids. Typically, we are working with enzymes or proteins which are in the range of 200 to 300 amino acids. So we are talking about roughly 3,000 atoms just for the enzyme. And then, since we are working in the classical world, we use explicit solvent. So we add solvent to this to solvate the enzyme. And then we end up with something around 30,000 atoms. So there's quite a lot of computational power involved here to do this. So actually simulating a protein folding or unfolding event takes time, really, really long time. I mean, if we were to spontaneously wait for an enzyme to fold or unfold, it would take, I mean, years on even the biggest supercomputer clusters, if it would ever happen. This is also a question of force fields. So the other part, of course, is that the free energy surface of these folding pathways are extremely complex. I mean, this picture is just an illustration, but I mean, this is not how it really would look. So the question that immediately comes to mind is, what is actually the unfolded state? So I said that we need to calculate the difference between the folded and the unfolded state. And then what is the unfolded state? I mean, what you do when you unfold a protein with computer simulations to speed up the process is to heat. So you increase the heat, and then the enzyme would start to unfold. But what would correspond to the unfolded state that you measure experimentally? So it's a difficult question to answer. So these pathways are complex, and we want to say something about the difference. And a sort of a little trick here, and it's also kind of intuitive, and it's that the free energy is state function. So we don't really need to focus on anything in between here. We are only interested in the endpoints. So the pathway from the folded to the unfolded state is relatively uninteresting to us, luckily. So we need an estimate for the denatured state and an estimate for the native state of our enzyme. And once we have this, we can use normal free energy perturbation to introduce the mutations. And then we can draw a thermodynamic cycle for this and do a little trick. So we have the folded enzyme, the wild type, so that contains no mutations. We can introduce a mutation and quite easily calculate the change in the free energy in the enzyme by introducing this mutation. And then we can take the unfolded enzyme and do the same here. So the denatured state, same mutation, and calculate the change in the free energy here. So the vertical lines on this thermodynamic cycle then would correspond to the folding or unfolding free energies of this enzyme. So by combining the two horizontal lines here, we can obtain an estimate for the protein stability here. So in free energy perturbation, we are calculating the free energy difference between two states. So we have a potential energy function representing state A and a potential energy function representing state B. And then we can use something that's called Swansig's formula, which is, the expression is very similar to the normal transition state theory expression. And then we can calculate the change in the free energy from these two potential energy functions. And the bracket here, you see this A here, so that means that we are averaging on the configuration for state A. And that is because in reality we are simulating on state A. And every time a new configuration is accepted, you're also calculating the energies of state B. But a criteria for this to work is that there has to be a certain overlap between the two potential energy functions, and this is normally not the case. So what we do to get this overlap is that we create a mapping potential. So we are doing an alchemical transformation between the two states. So we are sampling non-physical states and thereby making sure that we have a significant overlap between the two potential energy functions as we go from state A to state B. And then we can calculate the free energy as the sum of these Swansig formulas for every lambda window. It's really difficult to aim the mouse in here, but okay. And in order to actually mutate an entire amino acid into something else, I'm not going to go into details here, but then we have divided the FEP protocols up into something called sub-FEPs. So this involves doing smaller steps where we start with turning off charges and then the Jones potentials and thereby making the atoms gradually vanish. And in this example we have a tyrosine which is mutated to an alanine residue. So I mean if we were to go directly from this to this, our energies would explode. So I mean we would have no continuous overlap between the potentials. So this is part of the scheme that we have been working on lately in order to do this. So this is how it actually looks now. So we have an extended thermodynamic cycle, so that enables us to mutate any residue into something else by going through a common link here. So we would mutate anything, annihilate everything down to a C beta of the particular residue. So in this case we can go from an asparagine to the C beta, and then we can go from a tyrosine to the C beta. So the mutation would be asparagine to a tyrosine residue. And then we can predict the unfolding or folding free energy by combining the horizontal lines here. I should perhaps say that one of the crude approximations that we are doing here is that, so we do not know how the unfolded state looks. So we are taking out an amino acid sequence from the protein of only 3 amino acids. So we are using a 3-peptide here to approximate the unfolded state of the enzyme. We have tried with 1 amino acid, we have tried with 3, 6, 9, 12. The 3 seems to be working at least just as good as everything with more acids. And that 1 didn't give very good results. And little commercial break. So this tool has been implemented in QGUI, which is our graphical user interface for Q. We published the first version of QGUI in 2015, and now we are right around the corner to publish version 2, which includes several new features, and one of them is this tool, which is called ResFap, which allows you to calculate protein stability or ligand fat binding. It's everything that goes with fat binding that needs some sort of combining the. So right now we have 27 FEP schemes included in our library, so they have almost all amino acid mutations that you can think of with some modifications. And then what did we get? So we have been doing benchmark calculations on 4 different enzyme systems. We have included, these are more or less classical enzymes to do this type of calculations on. We have done it on Berna's chymotrypsin inhibitor 2 lysozyme, and an unknown protein to me, FF domain, a meta guy down in Uppsala who had been working experimentally on protein stability, and they have structures and data for this protein. So I haven't seen any computational studies on FF domain at least. So we picked out 5 to 6 mutations per protein with experimental stability values and tried to use them to benchmark this. Of course, the challenge here is that these are 4 different enzymes, 4 different labs, and also different experimental techniques. So we should not expect to get a perfect correlation. But this is what we got. So this is the plot for all. So we have the calculated delta G's on the y-axis and experimentally measured delta G's on the x-axis. And I think this looks pretty good. It's not perfect. It doesn't go through 0. But what we really are interested in still is the relative changes in stability upon doing mutations on the protein. And also considering that these are not from the same experiment, it's pretty good. Ideally all of these experimental values should have been done in one lab. That would have made it a better suited case, but that's not a luxury that we have in academia usually to get people to do stuff like that for you.
What are the units?
kcals per mole.
Okay.
But if we take out only one system, so this is lysozyme, so then we are not biased by the other, then the correlation is actually quite strong. So the FAT protocol that we have developed is doing a pretty good job in estimating the order of the stability calculations. So if something destabilizes the protein, it is fully reconstructed by the calculations. So that's a good thing, I think. So then is the question, what lies in the future for this? So we are continuously updating and improving our FEP protocols. Tor Arne has done a lot of work on the FEP protocol. And QGUI 2 is soon to be launched, so these calculations will be available for everyone. And of course, in the future, we would like to be able to design enzymes, that you really could think of a particular target and fit the enzyme to that target. But that's a long way ahead. But we are slowly getting there. Okay, that's it. Thank you for your attention.
We'll go ahead with some questions. We'll start with Daniel.
You showed this reduction of amino acids to common residues such as C-beta.
Mm.
Do you then really have a pure C-beta in there, or did you cap it with, say, hydrogen atoms or whatever?
Actually, that was a lie from my side. So it's not actually a C-beta, it's an alanine. So we actually mutate everything to an alanine. But we just call it a C-beta because that carbon atom is like the common growing point for our amino acids. But, yeah, maybe a good idea to put in alanine there instead. But the idea is that we should also have other common fragments than alanine. Not all residues need to be annihilated down to alanine.
Mm-hmm.
That would be a waste of computer resources.
So could you imagine that for arginine and phenylalanine you could maybe directly just exchange the hydrogen?
Yeah, but a simpler case is if you take tyrosine and phenylalanine.
Yeah, tyrosine, not
exactly.
not hydrogen.
Then it would be pretty wasted to go all the way down to alanine.
Yes.
Any more questions from Tromso? Okay, Daniel again.
Why don't you take glycine?
Yeah, that's a good question. Glycine is actually a bit more complicated because we have some torsional changes to the backbone, but that one should be doable. We haven't included it yet, but a more realistic problem is proline, so that one is not included.
Can you say something more about these 3 amino acids that were enough to model the unfolded state? How did you find out that it was good enough?
Well, we are not the first in the world to try this, so people have been trying to do these calculations in similar manners for years. And I mean, it's quite common to use either an alanine, X-alanine, where the X would be the actual residue. So we are using the actual sequence from the enzyme and also another method. But we tried in the beginning, we tried to step us up from 1 amino acid and all the way up to 12. And we saw so it sort of went up like this and nothing happened from 3 and out. So we didn't see any reason to try to include anything else. But I mean, so this will always be our excuse when we do not get a match with experimental values. It's because we do not really know how the actual unfolded state here looks.
So this is just a long chain in solvent?
Exactly, yeah, it's just a peptide chain in solvent.
So you talk about protein stability, and you talk about you need only the final and the folded and the unfolded state. But you also want to design enzymes, and in my mind, at least the transition state will also be important on whether it will be stable.
Yeah, you mean whether or not, if you lower the transition state between, I mean, enzymes are in general marginally stable anyway, so I mean, but I mean, if you by chance increase the transition state so it would never fold, that could be, good comment, and luckily I don't have to deal with this very soon, but it's a tricky topic.
Okay, Daniel again.
What was my question? You showed these models of potential energy surfaces where you said we have the enzyme and the denaturated form of the enzyme. Mm-hmm. And in these models you showed, the energy of the denaturated form was higher. Yes?
This one, yeah.
Is this just a cartoon, or is the denaturated form of the enzymes normally?
It can be, it doesn't have to be. But usually it's the opposite way around. I mean, usually the folded enzyme is lower. It actually is like that.
But what's then the driving force for denaturation? Why do these guys denaturate when the native form is lower in energy?
They don't.
Yeah, I mean, it is. I mean, like I said, enzymes are only marginally stable. So there's an equilibrium. They are going back and forward. It's not like it goes into this folded configuration and stays like that. I mean, even the folded configurations are. I mean, if you look on a crystal structure, it's just an average of many.
Okay.
Any more questions from Tromso? If not, then we go to Oslo.
Questions from Oslo, or? No, it doesn't seem like there is any questions from Oslo today.
No questions? Then this is the end of the presentation, so let's thank the speaker again. And I'd like to wish you all a nice weekend.